Beneath your feet, hidden from view, lies a world of immense forces and secret structures that shape everything from the ground you walk on to the very stability of the continents. We live on a planet whose most fundamental truths are invisible to our eyes, a reality we've accepted for all of human history. But what if you could pull back that curtain? What if you could see the unseen and hold a perfect, three-dimensional map of the planet's hidden architecture? This is no longer a question for science fiction. This is the new reality being painstakingly drawn by the silent architects of momentum autonomous drone fleets engineered to map the force of gravity itself. These are not mere flying robots, they are sophisticated sentinels working in perfect harmony to translate the planet's subtle whispers into a language we can finally understand. They are revealing the distribution of mass beneath our feet, from vast underground reservoirs of water to the dense ore bodies that power our civilization, and in doing so, they are fundamentally changing our relationship with the Earth. This journey we are about to take is not just about advanced machinery, it is about unlocking a new sense for humanity, a way to perceive our world through the lens of gravity. We will venture into the core technology that makes this possible, from the breathtakingly sensitive gravimeters that can feel a billionth of a change in gravity's pull, to the complex swarm intelligence that allows these drones to operate as a single, cohesive mind. We will uncover why this represents a pivotal breakthrough, a paradigm shift that is transforming the slow, arduous work of geophysics into a dynamic, high-resolution exploration. The implications of this shift are profound, touching every aspect of our modern world. It means finding vital natural resources with unprecedented precision, safeguarding our cities by understanding the ground they are built upon, and monitoring the alarming melt of polar ice with a clarity we have never before possessed. This is a story about turning the invisible into the actionable, about giving ourselves the tools to build a more secure and sustainable future. So prepare to dive deep into a world where the map is not of the surface, but of the forces that define it. We are about to uncover how these silent architects are decoding the planet's deepest secrets, one precise gravitational measurement at a time. This exploration will change how you see the ground beneath you, revealing a dynamic, living planet that has been waiting just out of sight, and setting the stage for a new era of planetary understanding that is just beginning. Think of a flock of starlings moving as one in a mesmerizing aerial ballet, a single entity made of many individual parts. Momentum drone fleets operate on a similar principle of collective intelligence, but their purpose is far more profound than creating beautiful patterns in the sky. These are highly specialized aerial systems where each individual drone is more than just a flying machine. It's a mobile scientific observatory. Their defining mission is to detect and map the incredibly faint variations in Earth's gravitational field, variations so subtle they are completely imperceptible to us, yet they hold the key to understanding the planet's hidden structure. This isn't about what the ground looks like, it's about what it's made of and how its mass is distributed deep beneath the surface. To grasp their unique nature, it's helpful to contrast them with the drones we're familiar with. A standard commercial drone might carry a camera for photography or a thermal sensor for search and rescue. Its value is in observing the surface. A momentum drone, however, is equipped with an entirely different kind of sensor, an ultra-sensitive gravimeter. Think of a gravimeter not as a camera for light, but as a precise scale that can weigh the planet's pull from the air. These instruments are so finely tuned they can detect a change in gravity equivalent to 1/1000th of the force you feel right now. But the drone itself is a source of motion and vibration, which creates tremendous noise that would overwhelm this delicate measurement. This is where the momentum part of their name becomes critical. The term momentum here refers to a carefully controlled and synchronized state of motion for the entire fleet. They aren't just flying fast, they are maintaining precise velocities, altitudes, and formations relative to one another. This coordinated movement is a form of active noise cancellation on a grand scale. By understanding their own motion with extreme precision, the drones can mathematically subtract the effects of their flight, the bumps from turbulence, the vibrations from their motors, from the gravitational data they are collecting. It's this ability to isolate the true gravitational signal from the chaotic background of flight that allows them to achieve a level of accuracy that was once thought impossible from an airborne platform. Without this sophisticated control over their collective momentum, the gravimeters would be useless, registering only the drone's own movement. Ultimately, these fleets represent a powerful fusion of three distinct technological frontiers: advanced robotics for autonomous flight, cutting-edge sensor technology for data acquisition, and complex data algorithms for processing and interpretation. They are a perfect example of a system where the whole is vastly greater than the sum of its parts. A single drone might give you a single data point, but a fleet operating in a coordinated swarm gives you a rich, multi-dimensional picture. They are, in every sense, the silent cartographers of an unseen world, drawing maps not of mountains and rivers, but of density and mass. This foundational role is fundamentally changing our relationship with the physical environment, allowing us to interact with the Earth based on a deep, quantitative understanding of its hidden architecture, an understanding that begins with the incredible instruments they carry aloft. To truly appreciate the magic happening inside these drones, we need to understand the two core instruments working in perfect harmony. First, let's talk about the gravimeter. Imagine trying to weigh a single grain of sand while you're on a roller coaster. That's the level of difficulty this device overcomes. It's not measuring weight in the traditional sense, but rather the local acceleration due to gravity. Modern airborne gravimeters, often based on superconducting technology or precise laser measurements of falling atoms, are so sensitive they can register a change of 1 gal. That's a change of 1/1000th of the gravity you're experiencing right now. This incredible sensitivity means it can feel the faint extra tug from a dense ore body deep underground or the slight weakening of gravity's pull over an empty aquifer. It's the primary sensor, the star of the show, but it's practically blind without its indispensable partner. That partner is the Inertial Navigation System, or INS. Think of this as the drone's hyper-aware internal sense of self. It's a complex package of gyroscopes and accelerometers that constantly measures every tiny movement of the drone, every tilt, every vibration, every bump from a gust of wind. It knows the drone's position, its velocity, and its orientation in three-dimensional space with astonishing precision, often down to a few centimeters. This is absolutely critical because the gravimeter, in its quest to feel the Earth's subtle pull, is also feeling all the violent motions of the flight. The raw signal from the gravimeter is a chaotic mess of data, dominated by the drone's own acceleration and deceleration. Without correction, this noise would completely drown out the tiny gravitational signal we're trying to find. This is where the technological marriage occurs. The data from the Inertial Navigation System is fed into powerful onboard computers. These computers perform a kind of digital subtraction. They use the precise motion data from the INS to calculate exactly how much of the gravimeter's signal is caused by the drone's own movement. Once that massive amount of noise is mathematically stripped away, What remains is the pure, clean gravitational signal emanating from the Earth below. This synergy is the alchemy that transforms a simple flying machine into a powerful geophysical probe. It's a continuous, real-time process of measurement and correction, a dance between two systems that allows us to perceive a fundamental force of nature from a moving platform in the sky. The result is data of unprecedented clarity and precision. This isn't just about detecting large, obvious structures. The combined system is so refined that it can map the gradual depletion of a groundwater basin over a season, pinpoint the exact location of a narrow mineral vein, or reveal the hidden geometry of a fault line deep within the Earth's crust. It gives us a kind of X-ray vision, but instead of seeing with radiation, we are seeing with gravity. This technological core is what empowers the entire mission, turning abstract theory into tangible, actionable intelligence about the world beneath our feet. Now, you might wonder why a single, highly advanced drone isn't sufficient for this task. After all, if one drone has a sensitive gravimeter and a precise navigation system, shouldn't it be able to gather all the data we need? The answer lies in a problem that has long plagued scientists: noise. A solo drone is like a single musician trying to play a complex symphony in the middle of a roaring stadium. It can hear its own instrument, but it's nearly impossible to pick out the subtle harmonies and melodies from the overwhelming cacophony of the crowd. In this case, the crowd noise includes constant minor interference like atmospheric turbulence, subtle changes in air pressure, and even tiny, inherent drifts within the drone's own sensors. These factors create a messy, blurred signal that obscures the very gravitational details we're trying to measure. This is where the principle of coordinated momentum transforms the entire endeavor. The power of the fleet isn't just in having more drones, it's in how they move together as a single, intelligent instrument. Imagine two drones flying side by side in a perfectly synchronized formation. They are both experiencing the same background noise, the same gust of wind, the same patch of turbulent air. However, the underlying gravitational signal from the Earth beneath them is slightly different because they are at two distinct points in space. By taking a differential measurement, essentially comparing the data from both drones at the exact same moment, the common noise that affects both of them cancels out. What remains is the clear, pure difference in the gravitational pull between those 2 points. This is the foundational advantage of the fleet. It's a form of active noise cancellation on a grand aerial scale. The term momentum in this context is also key, and it goes far beyond simple speed. It refers to the meticulously controlled and synchronized kinetic state of the entire swarm. Every drone's velocity, its acceleration, and its trajectory are precisely managed relative to every other drone. This isn't a loose group of aircraft, it's a cohesive array, a moving baseline of sensors. This coordinated movement allows scientists to treat the entire fleet as a single, massive, distributed sensor. The relative positions and motions of the drones become a known variable in a complex mathematical equation, an equation that solves for the Earth's density below. The momentum is the controlled variable that makes the entire differential measurement process possible and reliable. The result of this collaborative approach is a leap in data quality that is nothing short of revolutionary. A single drone provides a series of individual data points, like a handful of pins stuck in a map. A coordinated fleet, however, weaves those points into a rich, continuous tapestry. It provides the high-resolution data density needed to create a true three-dimensional model of the subsurface. Instead of just knowing that there's a dense object somewhere over there, the fleet can outline its precise shape, depth, and dimensions. This transforms the final output from a rough, interpretive sketch into a high-fidelity, photorealistic map of hidden geological structures. It's the difference between seeing a shadow and seeing the object itself, with all its intricate details and contours revealed. Now, this flood of raw numbers from the fleet is just the beginning. The real magic, the transformation of that chaotic data stream into a clear, three-dimensional picture, happens in the data fusion pipeline. Think of this as the most sophisticated digital darkroom imaginable, but instead of developing a photograph, it's developing a portrait of the Earth's hidden interior. Each drone is constantly streaming a river of information, not just gravitational readings, but its exact latitude, longitude, altitude, and every tiny jolt and tilt from its inertial navigation system. We're talking about terabytes of data for a single survey, an immense volume that would be utterly incomprehensible to the human eye. The first critical step is a digital cleansing process. Powerful algorithms act like noise-canceling headphones for the data, meticulously identifying and removing artifacts. They filter out the high-frequency vibrations from the drone's motors, the bumps caused by atmospheric turbulence, and any subtle drift in the sensors themselves. This leaves a much cleaner, but still very sparse, set of gravitational measurements tied to specific points in space. The next stage is where the true computational artistry begins, using a technique known as inverse modeling. This is a fascinating concept. In a traditional physics problem, you might be given a known object, say, a buried sphere of iron, and asked to calculate the gravitational field it would create at the surface. That's a straightforward or forward problem. But what we have here is the exact opposite. We've measured the gravitational field, and we need to work backwards to figure out what arrangement of materials underground must be causing it. This is the inverse problem, and it's notoriously tricky because countless different underground configurations could theoretically produce the same pattern of gravity readings at the surface. It's like being given a single shadow on a wall and trying to deduce the exact shape, size, and distance of every object casting that shadow. To solve this puzzle, geophysicists borrow a concept from medical imaging called tomography. You can think of it as a form of computational triangulation in 3 dimensions. Just as a CT scan takes many X-ray images from different angles to build a cross-sectional view of the human body, the drone fleet takes thousands of gravity measurements from different points above the ground. The system then uses complex mathematical models to essentially slice the subsurface into a vast 3-dimensional grid of tiny voxels, which are like the pixels in a 3D image. The algorithm then iteratively tests different density values for each of these millions of voxels, constantly comparing the resulting simulated gravitational field against the actual measurements taken by the drones. It's a process of intelligent trial and error, refined over millions of calculations until the simulated model and the real-world data align almost perfectly. The final output of this monumental computational effort is a dynamic, color-coded 3D gravity map. This isn't a static image, it's an interactive digital model that a geologist can rotate, zoom into, and slice through on a computer screen. Areas of high density, like a body of iron ore or dense bedrock, might glow in warm colors like red and orange. Regions of low density, such as a porous aquifer or an ancient lava tube, would appear in cool blues and purples. This visualization is the ultimate act of translation, turning abstract numbers into an intuitive, visual story of the subsurface. It reveals the hidden architecture of the Earth, the outlines of forgotten river channels now buried deep underground, the domes of salt that often trap reservoirs of oil, and the fractured zones in bedrock that could signal a potential landslide risk. This computational alchemy is the crucial final step. the key that unlocks the vault and makes the invisible forces shaping our planet not just measurable, but visible and understandable. This ability to map the unseen density of the Earth is fundamentally rewriting the playbook for how we discover the raw materials that fuel our civilization. For decades, the hunt for oil and gas has been a high-stakes, high-cost endeavor, often compared to finding a needle in a haystack while blindfolded. Companies relied heavily on seismic surveys, which involve setting off controlled vibrations at the surface and listening for the echoes from deep underground. While effective, this process is incredibly invasive. It requires heavy vehicle traffic across vast tracts of land, the clearing of vegetation for survey lines, and the generation of intense sound waves that can disrupt wildlife. It's also enormously expensive, with a single major survey running into the tens of millions of dollars. Now, enter the silent architects. Their three-dimensional gravity maps provide a powerful, non-invasive first look. They excel at identifying large-scale geological features that are prime real estate for hydrocarbons. A classic example is the salt dome. These massive plugs of buoyant salt push up through layers of sedimentary rock, often creating perfect, dome-shaped traps that capture oil and natural gas. On a gravity map, a salt dome stands out clearly as a low-density anomaly against the denser surrounding rock. By pinpointing these structures from the air with drone fleets, exploration companies can drastically narrow their focus, using seismic technology only in the most promising areas. This triage approach saves an immense amount of time, money, and environmental disturbance, turning a scattershot search into a precisely targeted investigation. The revolution is equally profound in the mining industry. The global demand for minerals like copper for electronics, lithium for batteries, and rare earth elements for renewable energy technology is skyrocketing. The easy-to-find surface deposits have largely been discovered, forcing miners to look deeper beneath layers of barren rock. Traditional exploration involves painstaking soil sampling, geological mapping, and a great deal of guesswork, followed by a costly campaign of drill holes. Many of these holes come up empty, representing a massive financial loss. Gravity mapping flips this model on its head. Dense ore bodies, such as those rich in iron, copper, or gold, create a distinct gravitational signature, a localized high-density bullseye on the map. A drone fleet can survey a massive, remote concession in a matter of days, producing a map that highlights these bullseyes with startling clarity. This allows geologists to place their first drill holes with unprecedented confidence, directly targeting the highest probability zones. The result is a dramatic increase in discovery rates and a significant reduction in the number of unsuccessful drill sites, which means less scarring of the landscape and a much smaller environmental footprint for the same mineral yield. The economic and environmental implications of this shift are staggering. Exploration is the riskiest phase of any resource project, often consuming billions of dollars with no guarantee of a return. By making discovery more efficient and reliable, this technology de-risks the entire industry. It channels investment capital more effectively and accelerates the development of new mines and oil fields that are crucial for economic growth and technological advancement. From an environmental perspective, the benefits are twofold. First, the method itself is remarkably low impact. A fleet of quiet, electric drones flying high above causes minimal disruption to the ecosystem below, a stark contrast to the rumble of seismic trucks or the extensive land clearing for exploration trenches. Second, by ensuring that drilling is only done where it is most likely to succeed, we avoid pockmarking the wilderness with unnecessary boreholes. This represents a move towards a more intelligent, more sustainable form of resource extraction, one that gets what we need with far less waste and damage. The silent architects, therefore, are not just tools for profit. They are becoming essential partners in building a more efficient and environmentally conscious pathway to securing the materials that power our modern world. While we often search for hidden minerals or energy sources, there is a resource far more fundamental to life itself that these drone fleets are helping us manage with newfound precision: our freshwater. Beneath the surface of the Earth lies a vast, hidden ocean stored in porous rock formations known as aquifers. These are not underground lakes, but more like massive, water-logged sponges, and they provide drinking water for billions and irrigate much of the world's agriculture. The critical challenge has always been understanding their health. How much water do they actually hold? Is that volume increasing from rainfall or snowmelt, or are we draining them faster than they can recharge? For decades, answering these questions meant relying on a scattered network of monitoring wells, like trying to understand the flow of an entire river by dipping a cup in at only a few random points. The data was sparse, localized, and often failed to capture the complex, large-scale dynamics of an entire aquifer system. This is where the silent architects reveal their profound value for hydrology. The principle is beautifully simple in theory, yet it requires their exquisite sensitivity to execute. Water has mass, a great deal of it. When an aquifer is full, the sheer weight of all that water in the subsurface creates a slightly stronger gravitational pull at the surface above it. When that same aquifer is depleted by pumping for farms and cities, the mass decreases and the local gravitational field weakens by a corresponding, almost infinitesimal amount. These changes are far too small for any human to feel, but they are perfectly detectable by the gravimeters on these coordinated drone fleets. By flying the same precise grid pattern over a watershed season after season, or year after year, the fleets can measure these subtle gravitational shifts. Each survey acts as a snapshot of the aquifer's total water storage at that moment. When you string these snapshots together, you get something revolutionary: a four-dimensional model. This isn't just a static 3D map of the aquifer's structure. It's a dynamic movie that shows the water levels rising and falling over time. You can literally watch the pulse of the watershed, seeing where recharge is happening most effectively, and critically, where over-extraction is creating a deep and sustained deficit. The practical applications of this living map are transforming water management, especially in arid and semi-arid regions where every drop counts. Consider a state like California or a country like India, where agriculture depends heavily on pumping groundwater. Historically, water managers had to make difficult allocation decisions based on incomplete data, often leading to overuse that went unnoticed until wells ran dry and the land itself began to sink, a phenomenon known as subsidence. Now, with a clear, quantitative picture of the entire groundwater basin, agencies can see exactly which farming districts are drawing down the aquifer most severely and which areas are benefiting from natural recharge. This allows for truly informed and equitable water policy. They can implement targeted conservation measures, manage recharge projects that deliberately funnel surface water back into the aquifer, and set sustainable pumping limits based on the actual capacity of the system rather than on guesswork. It turns water management from a reactive crisis response into a proactive, science-driven stewardship of a vital common resource. Furthermore, this technology provides an early warning system for droughts that is unlike any other. While we can see a lack of rain and measure low levels in rivers and reservoirs, the hidden groundwater reserve has always been a mystery until it was too late. With regular drone fleet surveys, managers can detect a developing groundwater drought long before it manifests in dry wells. They can see if the winter snowmelt is failing to recharge the aquifers adequately, allowing them to alert farmers and municipalities months in advance that a shortage is looming. This lead time is invaluable. It enables communities to implement water conservation measures early, to explore alternative water sources, and to prepare for potential shortages, thereby mitigating the worst social and economic impacts of a severe drought. The silent architects, therefore, become sentinels of water security, giving us the foresight we need to navigate an increasingly volatile climate. Their ability to quantify the invisible movement of water beneath our feet represents one of the most significant advances in environmental monitoring of our time, providing a foundational tool for building a more resilient and water-wise future. The ground beneath a modern city is a complex and often forgotten landscape, a hidden world of geology and history that holds the key to its structural destiny. For centuries, the primary method for understanding this subsurface realm before a major construction project has been the soil borehole. A drilling rig arrives on site, pulls up a narrow core sample of Earth, and gives engineers a precise but extremely limited snapshot of the ground conditions in that one specific spot. It's like trying to understand the entire plot of a novel by reading a single, random sentence. You might get lucky and hit a crucial piece of information, but you're just as likely to miss the overarching story entirely. The vast, weak zone of unstable clay running just meters to the left, or the forgotten network of an old coal mine silently collapsing 50 meters below. This localized data creates a dangerous illusion of knowledge, leading to designs that are based on incomplete and potentially misleading information. The consequences of this blind spot can be catastrophic, from the slow, expensive sinking of a building's foundation to the sudden, tragic collapse of a roadway into a sinkhole. This is where the macro-scale vision of a gravity mapping drone fleet changes the entire paradigm of geotechnical engineering. Instead of a handful of pinpricks of data, these silent architects provide a comprehensive, three-dimensional MRI of the entire project area. They reveal the large-scale geological structures that boreholes can easily miss. For instance, when planning a new suspension bridge, the placement of its massive anchorages is one of the most critical decisions. A gravity survey can identify subtle weaknesses in the bedrock that would be invisible from the surface, ensuring these colossal concrete anchors are founded on solid, competent rock that can handle the immense tensile forces for the lifetime of the bridge. Similarly, when routing a new subway tunnel, the map can reveal fissures in the rock, hidden water channels, or unstable, loose fill areas that could lead to a cave during excavation. This foreknowledge allows tunnel boring machines to be rerouted or for engineers to design specialized reinforcement plans before a single scoop of earth is removed, preventing costly delays and protecting worker safety. The value of this technology extends beyond preventing future disasters. It also involves solving mysteries from the past. In many older industrial cities, the historical records of mining activity are incomplete or have been lost to time. The ground beneath these urban areas can be a Swiss cheese of abandoned shafts and tunnels, lurking unknowns that pose a permanent threat. A classic and tragic example is the 1995 collapse of a department store in Seoul, South Korea, which was built on the site of a backfilled reservoir without adequate ground support. A gravity survey from a drone fleet is uniquely capable of detecting these man-made voids. The air-filled space of an old mine shaft or a crumbling cellar creates a pronounced low-density anomaly, a clear signature of danger on the gravity map. By identifying these hidden hazards, cities can proactively stabilize the ground or mark these zones as non-buildable, turning potential future disaster sites into public parks or green spaces, thereby safeguarding lives and property. For the urban planners who shape the growth of our metropolitan areas, This subsurface intelligence provides a powerful new layer of data for making strategic, long-term decisions. A gravity map effectively classifies the land itself based on its inherent stability and load-bearing capacity. Planners can use this information to create a scientifically grounded development suitability map. Zones with deep, stable bedrock can be confidently designated for high-density skyscrapers and critical infrastructure. Areas that show a high potential for sinkholes or liquefaction during an earthquake can be zoned for low-impact uses like agriculture, recreational parkland, or single-story residential buildings with lightweight foundations. This macro-scale view moves urban planning from a reactive process, often driven by developer interest and political will, to a proactive, evidence-based practice that respects the fundamental geology of the region. It is a cornerstone of building resilient cities that can withstand the test of time and the growing pressures of climate change and population growth, ensuring that the silent architects of today lay the groundwork for the safe and sustainable cities of tomorrow. While drone fleets are transforming industries and safeguarding our infrastructure, their impact resonates on a far grander scale, reaching into the very heart of planetary science. For geologists, these silent architects are not just tools for resource management. They are time machines and X-ray vision rolled into one, offering an unprecedented window into the deep, dynamic processes that have sculpted our world over billions of years. Consider the immense, slow-motion collision of tectonic plates. We can map the surface fault lines, and we can feel the earthquakes they generate. But understanding the full three-dimensional structure of a subduction zone, where one plate dives beneath another, has always been like trying to understand a car crash by only looking at the dented fenders. Now, with gravity mapping fleets, scientists can create detailed density models that reveal the descending slab of oceanic plate as it plunges dozens, even hundreds, of kilometers into the mantle. These models show how the slab bends, cracks, and interacts with the surrounding rock, helping to explain the distribution of deep earthquakes and the formation of volcanic chains above. This is akin to finally being able to see the entire wreckage, the twisted frame, and the displaced engine, giving us a complete mechanical understanding of the planetary forces at work. This powerful new vision also allows us to excavate the past without a single shovel. Majestic mountain ranges like the Himalayas or the Andes are merely the surface expression of vast, deep-seated roots that extend far down into the crust and upper mantle, much like the submerged bulk of an iceberg. The theory of isostasy suggests that mountains have these deep roots, less dense crustal material buoyantly projecting downward into the denser mantle to support the weight of the peaks above. For the first time, gravity mapping provides direct, high-resolution evidence of these subterranean foundations. By analyzing the subtle gravitational variations across a mountain belt, geophysicists can map the precise geometry and depth of these roots. This data reveals the hidden architecture of ancient, eroded mountain ranges that have long since vanished from the surface, their ghostly roots still preserved in the deep crust, telling a story of colossal continental collisions that happened hundreds of millions of years ago. It's a form of planetary archaeology, reading the history of Earth's most dramatic upheavals from the enduring signature of their mass. Perhaps one of the most critical and hazardous geological features we can now probe with new clarity is the volcanic system. Traditional monitoring relies on surface measurements, gas emissions, ground deformation, and seismic rumblings. These are vital, but they are symptoms of a deeper, hidden process. A gravity mapping fleet flying a time-lapse survey over an active volcano like those in Iceland or Japan can detect something far more telling: the movement of magma itself. As molten rock accumulates in vast subterranean chambers, its dense mass creates a growing gravitational anomaly. By measuring the increase in this pull over time, scientists can estimate the volume of new magma intruding into the system, providing a crucial early warning of potential eruption. Conversely, after an eruption, a decrease in gravity signals the emptying of those chambers. This ability to track the underground fuel supply of a volcano represents a quantum leap in our predictive capabilities, moving us from reacting to volcanic unrest to proactively modeling the internal pressure buildup that leads to it. All of this deep probing culminates in a revolutionary new ability to test the grand foundational theories of geology. The concept of mantle plumes hypothetical, towering upwellings of superheated rock from the deep mantle that are thought to create volcanic hotspots like Hawaii has been debated for decades. Does a true, narrow plume feed these islands, or is the volcanism caused by more shallow processes in the crust? A detailed 3D gravity model of the entire region can reveal the telltale density signature of such a plume, a column of buoyant, less dense material reaching down through the mantle. By creating these detailed models of the crust and upper mantle, scientists are no longer relying on indirect clues. They are building tangible, three-dimensional representations of our planet's inner workings. This technology is fundamentally validating or reshaping our understanding of continental drift, mantle convection, and the very engine of plate tectonics. It offers a new way to see deep into the Earth, not by digging a hole, but by precisely weighing the planet's hidden compartments, opening a bold new frontier in our quest to understand how our world formed, how it evolves, and how it will continue to change. This profound scientific pursuit, focused on Earth's deep time, finds an urgent and direct parallel in the most pressing issue of our present, the rapid and alarming changes to our global climate. The vast frozen domains of Greenland and Antarctica hold a secret that is central to our planet's future, a secret locked not just in the ice itself, but in the invisible force it commands. We often think of glaciers and ice sheets as static, majestic landscapes, but in the context of climate change, they are dynamic and rapidly changing reservoirs of mass. Their sheer scale is almost incomprehensible. The Antarctic ice sheet alone contains enough water to raise global sea levels by over 60 meters. This titanic volume of frozen water exerts a tremendous gravitational pull on the surrounding ocean. Think of it as a planetary scale magnet. The ocean is literally drawn up and towards the ice, creating a subtle hill of water along the coastlines of Greenland and Antarctica. This is a fundamental principle of physics. Mass attracts mass. For centuries, this gravitational relationship has been a stable feature of our planet, but now human-induced global warming is violently disrupting this equilibrium. As these colossal ice sheets melt at an accelerating pace, they are not just adding water to the ocean, they are fundamentally altering the Earth's gravitational landscape in their regions. When billions of tons of ice vanish from the land and flow into the sea, the local mass decreases. This loss of mass means the ice sheet's gravitational pull weakens. It's like the planetary magnet is losing its strength. The immediate, counterintuitive consequence is that sea levels near these melting ice sheets can actually drop. The ocean, no longer being pulled as strongly towards the ice, sloshes away, redistributing itself across the global ocean. This phenomenon makes predicting sea level rise far more complex than simply adding meltwater to a bathtub. It's a three-dimensional puzzle of gravity, rotation, and the Earth's elastic response, a puzzle that traditional satellite altimetry, which measures sea surface height from space, struggles to solve with fine-grained detail. This is precisely where the silent architects enter the stage, offering a perspective that was previously out of reach. Deploying a coordinated fleet of these drones over the harsh, Remote polar regions allow scientists to measure this gravitational weakening with a spatial resolution that satellites simply cannot match. While satellites like the GRACE mission have provided invaluable data on global gravity changes, their footprint is broad, covering areas hundreds of kilometers across. A drone swarm flying precise, low-altitude patterns over a specific glacier system like Thwaites in Antarctica or Jakobshavn in Greenland can pinpoint exactly where the ice loss is most severe. They can measure the gravitational signal from individual glacial valleys and outlet streams, distinguishing between the mass loss from surface melt and the much more rapid and dangerous loss from ice shelves collapsing into the sea. This granular data provides direct, irrefutable, and quantifiable evidence of ice mass loss, transforming a global trend into a localized, measurable event. It tells us not just that the ice is melting, but precisely where and at what rate, turning abstract climate models into concrete, observable facts on the ground, or rather, in the air. This gravitational intelligence does more than just document the problem. It dramatically improves our ability to forecast its consequences. The meltwater from Greenland and Antarctica doesn't just raise sea levels uniformly. Because of the gravitational changes and the complex dynamics of ocean currents, the sea level rise will be uneven across the planet. For example, when a major portion of the Greenland ice sheet melts, the local sea level around Greenland might fall, but the eastern seaboard of the United States could experience a rise that is significantly greater than the global average. Similarly, the melting of West Antarctic ice could disproportionately impact coastlines in the Pacific. By combining the high-resolution gravity maps from drone fleets with sophisticated ocean circulation models, scientists can now create far more accurate and region-specific sea level rise projections. This is critical information for coastal cities from Miami to Mumbai, from Shanghai to Sydney. It allows urban planners and governments to make multi-billion-dollar decisions about building seawalls, relocating infrastructure, and developing adaptation strategies with a much clearer understanding of the specific threat their community will face. The drone's data helps paint a detailed picture of our future coastline, not with broad, alarming strokes, but with precise, actionable contours. In this monumental struggle to understand and mitigate climate change, these autonomous fleets have become vital sentinels. They are our eyes on the ground in the most inaccessible places on Earth, providing a continuous, detailed stream of truth about the health of our cryosphere. They move beyond simply proving climate change is happening. They are quantifying its mechanics with stunning precision, allowing us to move from a stance of general concern to one of specific, data-driven response. They bear witness to the Earth's shifting balance, measuring the retreat of ancient ice not just in kilometers, but in the faint ebb and flow of gravity itself. This role as a precise monitor of planetary change is perhaps their most profound application, turning them from mere technological tools into essential partners in safeguarding our collective future. The success of this crucial mission, however, depends entirely on a complex and invisible dance of autonomy happening in the sky above the ice, a dance governed not by human hands but by artificial intelligence. The sheer scale of managing these airborne fleets presents a logistical puzzle that the human mind simply cannot solve in real time. Directing dozens or even hundreds of individual drones would require an army of pilots and air traffic controllers, each struggling to process a flood of data and coordinate movements down to the centimeter. It would be chaotic, inefficient, and dangerously prone to human error. This is precisely where the invisible hand of artificial intelligence takes the controls, transforming a potential swarm of individual aircraft into a single, cohesive scientific instrument. The AI doesn't just issue commands, it functions as the fleet's central nervous system, a dynamic brain that processes information from every drone simultaneously. It constantly recalculates optimal flight paths, adjusting for wind shear, turbulence, and the precise positioning needed for the gravity measurements. Its primary objectives are a delicate balancing act, maintaining the perfect formation for data collection, ensuring no two drones ever come dangerously close, and guaranteeing that every single square meter of the survey area is covered without gaps or wasteful overlaps. This isn't a pre-programmed flight plan. It's a living, breathing, adaptive process that unfolds second by second, a symphony of motion conducted by algorithms. The magic that enables this complex coordination is rooted in a fascinating concept known as swarm intelligence. This isn't about a single, all-powerful computer dictating every move. Instead, it's about empowering each drone with a simple set of behavioral rules, much like those observed in a flock of birds or a school of fish. An individual bird doesn't have a grand plan for the entire flock's intricate maneuvers. It simply follows a few core principles: stay close to your neighbors, match their speed, and avoid collisions. From these simple, localized interactions, the breathtakingly complex and fluid motion of the entire flock emerges. The drone fleet operates on the same decentralized principle. Each unit is programmed with fundamental directives: maintain a specific distance from your designated neighbors, keep pace with the group, and prioritize obstacle avoidance. The AI provides the overarching mission parameters, but the intricate dance of the swarm arises from the bottom-up interactions between the drones themselves. This approach is not just elegant, it's incredibly robust and resilient. This resilience is the system's greatest strength, turning potential failure into a minor, self-correcting event. In a centrally controlled system, the failure of a single unit could cripple the entire operation. But in a swarm intelligence model, the loss of one drone is handled organically by the collective. Imagine a drone's battery running low or a sudden mechanical fault forcing it to return to base. The moment it drops out of formation, the drones around it immediately sense the change in their local environment through their relative positioning data. Their simple rules: maintain formation density, trigger an automatic response. They seamlessly adjust their own flight paths to close the gap, redistributing themselves to cover the missing drone's data collection area. The fleet effectively heals itself, maintaining the integrity of the scientific survey without any need for human intervention or a pause in operations. This emergent behavior ensures that the mission continues uninterrupted, making the entire system far more reliable and cost-effective than any human-piloted alternative could ever be. The level of autonomy achieved through this fusion of AI and swarm intelligence is the cornerstone that makes ambitious, large-scale gravity mapping not just a theoretical possibility, but a practical reality. It eliminates the astronomical cost and complexity of human-centric control, allowing a single ground crew to manage a vast fleet. This autonomy also enables a precision that is simply unattainable through manual control. The algorithms can execute flight patterns with a geometric exactness that perfectly suits the mathematical models used in the subsequent data processing, ensuring the cleanest, most consistent gravitational readings possible. Without this intelligent, self-governing coordination, the entire endeavor would be mired in logistical nightmares and prohibitive expenses, confining this powerful technology to small-scale demonstrations rather than the continent-spanning surveys it is capable of today. This self-directed capability to generate such profoundly detailed and valuable information, however, immediately propels us into a critical conversation about the stewardship and security of that very data. The incredibly detailed maps these drone fleets produce are far more than just scientific curiosities. They represent a new form of strategic intelligence, a digital X-ray of a nation's very foundation. Imagine a three-dimensional model that doesn't just show mountains and rivers, but precisely locates a massive, untapped aquifer that could sustain a country for decades, or pinpoints a rare earth mineral deposit critical for manufacturing advanced electronics. This same data could inadvertently reveal the location of a hidden underground military command center by identifying the large, man-made void it occupies, or expose geological weaknesses along a border region that could be exploited for strategic advantage. The value of this information is immense, placing it squarely in the realm of national security and economic competitiveness. This reality forces us to confront a series of critical and complex questions that extend far beyond the laboratory. Who actually owns the gravity data collected over a particular territory? If a private company from one nation flies its drone fleet over another country with permission to conduct a survey, does the data belong to the company that collected it, the government that owns the airspace, or the people who live on the land? The answers are not straightforward and can lead to significant international disputes, turning geophysical data into a potential tool for geopolitical leverage. This brings us to the crucial issue of data security. The vast digital libraries storing these subterranean maps are incredibly high-value targets for cyberattacks. A state-sponsored hacker could attempt to steal this data to gain an economic edge in global resource markets or to understand a rival's military preparedness. Conversely, a malicious actor could seek to corrupt or delete the data, sabotaging a multi-million-dollar exploration project or creating false maps to misdirect a nation's development efforts. Protecting this information requires a digital fortress built on the most robust encryption protocols available, often exceeding the standards used for financial transactions. Data must be encrypted not only when it's stored on secure servers, but also during its transmission from the drones back to the processing centers. Furthermore, access to the final interpreted maps must be governed by strict, multi-layered authorization protocols, ensuring that only vetted individuals with a legitimate need can view the most sensitive findings. This is not merely an IT problem. It is a fundamental requirement for the responsible deployment of the technology, as a single major breach could undermine global trust in the entire industry. Navigating this complex digital landscape is as vital to the mission's success as navigating the physical airspace. To prevent this powerful capability from becoming a source of international conflict, the development of clear international frameworks and agreements is essential. These frameworks need to establish common standards for data ownership, usage rights, and cross-border data sharing for scientific purposes. They must outline the rules of engagement, specifying under what circumstances a nation must grant access to its airspace for such surveys and what rights it retains over the resulting data. Organizations like the United Nations or international geophysical bodies could play a key role in facilitating these discussions, promoting a spirit of collaboration over competition. The goal is to create a global environment where this technology can be used openly for beneficial purposes, like collaborative climate research or managing transboundary water resources while respecting national sovereignty and protecting sensitive information. Establishing these rules of the road early on is critical to ensuring that the silent architects of momentum become a force for global understanding and cooperation, rather than a new frontier for tension and espionage. To truly grasp the revolutionary nature of these drone fleets, we have to travel back in time to the era before they existed, to the slow and arduous world of traditional gravity mapping. The classic method was a ground-based operation, and it was a feat of pure endurance. Teams of geophysicists would trek into the field, hauling gravimeters that were not just sensitive, but also incredibly heavy and cumbersome, often weighing as much as a person. These instruments had to be carefully leveled and stabilized on the ground at predetermined survey points, sometimes spaced kilometers apart. At each point, the team would wait patiently, sometimes for half an hour or more, for the instrument to settle and take a single, precise reading. This process was then repeated, point by painstaking point, across the entire survey area. It was the scientific equivalent of creating a massive, pointillist painting, but where each tiny dot required a long, difficult hike to place. The logistical challenges were immense. Dense rainforests, rugged mountain ranges, vast deserts, and swampy wetlands were often completely off-limits, as transporting this delicate, heavy equipment through such terrain was practically impossible. And of course, the oceans, which cover most of our planet, were an almost total blank spot for this kind of detailed ground survey. The result was a patchwork of data, a collection of disconnected dots on a map that required a great deal of guesswork to connect, leaving vast gaps in our understanding of the subsurface. The next evolutionary step was the move to the skies with airborne surveys, which offered a way to cover larger and more inaccessible areas. This involved mounting a gravimeter inside a manned aircraft, like a small plane or helicopter. While this was a significant improvement over ground surveys in terms of coverage, it introduced a whole new set of limitations. Manned aircraft are incredibly expensive to operate. You have the costs of the aircraft itself, the fuel, the pilot, and the support crew. Flight durations are limited by human fatigue and fuel capacity, making it difficult to cover truly massive areas in a single campaign. Furthermore, these planes had to fly at higher altitudes for safety and efficiency, which meant the gravitational signal they were trying to measure was weaker and more diluted by the time it reached the sensors. They also couldn't fly in the tight, coordinated formations needed for the differential measurements that drone swarms excel at. The data collected was like a slightly out-of-focus photograph covering a large area. You could see the broad shapes and outlines, but the fine details, the subtle textures that often held the most critical information, were lost in a blur. It was a better tool, but it was still a blunt instrument compared to the surgical precision we have today. Now, contrast that entire history with the modern approach of the coordinated drone fleet. The difference isn't just incremental, it's a complete transformation of the entire workflow. Speed is the most immediate and dramatic change. A survey that would have taken a ground team an entire field season, or a manned aircraft several weeks, can now be completed by a drone fleet in a matter of days. This isn't just about convenience, it's about capturing a snapshot of a dynamic Earth system before it changes. For monitoring groundwater or glacial melt, this speed allows for near real-time assessment. The cost savings are equally transformative. Without the need for large crews, expensive manned aircraft, and extended logistics, the price of a high-resolution gravity survey has plummeted, making this powerful tool accessible to smaller companies, university research groups, and developing nations. This democratization of data is a game-changer in itself, but perhaps the most profound advantage lies in the data quality itself. The drone fleet approach represents a fundamental paradigm shift in the very philosophy of measurement. We have moved from a world of point-based sampling to a world of continuous, high-density spatial mapping. Instead of a handful of disconnected data points, the drones create a rich, flowing river of information. Flying at low altitudes and in tight formations, they capture the gravitational field with a resolution that was once unimaginable. It's the difference between trying to understand a symphony by hearing only a few random notes played every minute and hearing the entire piece performed from the front row. This continuous stream of data allows algorithms to paint a seamless, high-fidelity picture of the subsurface, revealing intricate geological features that would have been completely invisible on a traditional point-and-connect map. This leap in data richness dramatically accelerates the pace of geophysical discovery, turning what was once a slow, plodding science into a dynamic, rapid-fire process of exploration and insight, opening the door to monitoring our planet with a frequency and clarity that was once the stuff of science fiction. When we talk about the price tag of a full-scale momentum drone fleet, it's easy to focus on the immediate sticker shock. Developing and deploying a complete system with its sophisticated gravimeters, swarm intelligence software, and data processing infrastructure represents a major capital expenditure, often running into the tens of millions of dollars for a single large-scale operation. It's a number that can make any corporate board or government minister pause, but to view this solely as a cost is to fundamentally misunderstand its economic nature. This is not an expense in the traditional sense. It is a strategic investment that pays for itself many times over by systematically eliminating waste, de-risking massive projects, and unlocking new efficiencies across entire sectors of the economy. The most compelling evidence for this comes from the high-stakes world of natural resource exploration. In the mining industry, for example, the success rate for moving from a prospective area to a commercially viable mine is notoriously low, often cited at less than 1%. This means that for every 100 drill holes sunk into the ground, 99 are essentially expensive failures, each one costing hundreds of thousands or even millions of dollars. A drone fleet's gravity map acts as a powerful pre-screening tool, dramatically increasing the odds of success. By clearly highlighting the most promising, dense anomalies, it allows geologists to place their first drill holes with surgical precision. The financial impact is staggering. If a fleet costs $15 million to deploy but prevents just 20 unnecessary drill holes at $1 million each, the system has already paid for itself, and the subsequent discovery of a single major ore body represents pure economic upside that might have otherwise been missed for years or even forever. The ripple effects extend deeply into the oil and gas sector, where exploration budgets are even more colossal. A single offshore exploration well in a deep-water environment can easily exceed $100 million. The decision on where to drill is perhaps the most critical financial decision an energy company makes. Traditional methods relying on broad seismic surveys still leave a great deal of uncertainty. By integrating high-resolution gravity data, companies can identify the most promising structural traps with far greater confidence. Avoiding just one dry hole in a complex geological setting can save enough capital to fund the entire drone fleet program for a decade. Furthermore, the efficiency gains continue long after discovery. During the extraction phase, detailed subsurface maps help engineers optimize the placement of production wells, maximizing the amount of resource recovered from a field. This increases the ultimate recovery factor, which translates directly into billions of dollars of additional revenue from the same asset. The economic argument, therefore, isn't just about avoiding losses. It's about actively boosting the productivity and longevity of the very resources that underpin our global economy. For the public sector, the economic calculus is just as powerful, though it manifests in the avoidance of catastrophic failures and the optimization of public works. Consider the immense cost of a major infrastructure project that goes wrong. The infamous sinking of the Millennium Tower in San Francisco, a luxury skyscraper that has tilted and sunk significantly, has led to remediation costs and lawsuits totaling over $1 billion. A comprehensive gravity survey conducted before construction could have identified the unstable, compressible soil layers that contributed to the problem, allowing for a different design or location. Similarly, the sudden collapse of a bridge or a section of highway due to an undetected sinkhole or subsurface void results in not only tragic loss of life, but also immense economic disruption from closed transportation routes and staggering reconstruction bills. The cost of proactively mapping a city's subsurface with drone fleets before approving major projects is a tiny fraction of the potential cost of a single engineering disaster. This proactive intelligence allows governments to allocate taxpayer money more effectively, ensuring that infrastructure investments are built on solid ground, both literally and fiscally, and are designed to last for generations without requiring constant, expensive repairs. The economic value also flows powerfully through our most vital resource, water. In agricultural regions which consume the vast majority of the world's freshwater, inefficient water use is not just an environmental concern, it's a direct drain on the economy. When farmers lack accurate data on aquifer levels, they often overpump as an insurance policy against drought, depleting the shared resource and increasing their own energy costs. With precise, seasonal gravity maps provided by drone fleets, water districts can implement smart allocation systems. Farmers can be given clear, data-driven quotas, ensuring the aquifer's sustainability. This prevents the economic devastation of a well field running dry, which can wipe out an entire season's crops and bankrupt farming communities. For municipal water systems, the ability to detect leaks in vast underground aqueducts or to map the precise boundaries of a protected watershed saves enormous sums. A single, undetected major leak can waste millions of gallons of treated water, representing a direct financial loss. By providing a macro view of the entire water system's health, this technology enables a shift from reactive, emergency-level fixes to proactive, cost-effective management, securing water for economic activity and community health. When we pull back to a macroeconomic perspective, the widespread deployment of these silent architects begins to look less like a technological upgrade and more like a fundamental piece of critical national infrastructure. A nation that can map its resources with precision enhances its resource security, reducing its reliance on volatile international markets. A nation that can build resilient, well-planned infrastructure attracts more business investment and fosters sustainable growth. A nation that can manage its water wisely safeguards its agricultural output and prevents drought-related economic shocks. The initial investment in the technology is dwarfed by the compounded economic benefits of a more efficient, safe, and predictable operating environment across multiple key industries. This financial viability creates a powerful feedback loop, where the savings and new revenues generated by early adopters fuel further research and development, leading to the next wave of innovation in the hardware that makes it all possible. The journey to fitting a gravimeter onto a drone is a story of physics and engineering overcoming immense odds. For most of the 20th century, a scientific-grade gravimeter was a massive, temperamental beast of an instrument. Picture a device the size of a large refrigerator, weighing several hundred kilograms and requiring a stable, vibration-free concrete pier sunk deep into the ground just to operate. It was so sensitive that even the footsteps of a person walking nearby could send its readings into chaos. Taking such a device into the field was a monumental undertaking. It required dedicated trucks, cranes, and a team of specialists to set it up for a single, stationary measurement. The idea of putting one on a platform that is inherently unstable, a vibrating, accelerating, and tilting aircraft was considered pure fantasy. The instrument itself would be its own worst enemy, registering its own violent motion far more strongly than the subtle gravitational tug from the Earth below. This fundamental incompatibility between the sensor's needs and the platform's nature was the primary barrier that kept airborne gravity mapping confined to much larger, smoother flying manned aircraft for decades. The breakthrough began with a shift in the underlying physics used to measure gravity, moving from mechanical springs to the strange and predictable world of quantum mechanics. The development of quantum gravimeters, particularly those based on cold atom interferometry, marked a pivotal turning point. These devices don't rely on a physical spring stretching or compressing. Instead, they use lasers to cool a cloud of atoms to a fraction of a degree above absolute zero, effectively making them almost completely motionless. This cloud of atoms is then dropped in a vacuum chamber, acting as a perfect friction-free test mass. By precisely measuring how these falling atoms are affected by gravity using laser light, these sensors can achieve astounding accuracy. Because they are based on fundamental atomic properties, they are inherently more stable and less prone to the long-term drift that plagued their mechanical ancestors. This quantum leap in technology wasn't just about improving accuracy. It was about redefining what a gravimeter could be: smaller, more robust, and finally, mountable on a dynamic platform like a drone without being overwhelmed by noise. Simultaneously, a parallel revolution was happening at the microscopic scale with micro-electromechanical systems, or MEMS. This is the same technology that gives your smartphone its ability to sense rotation for screen orientation and step counting. MEMS devices are tiny mechanical elements like microscopic springs and weights etched directly onto a silicon chip. For gravimetry, researchers began developing incredibly sensitive MEMS accelerometers that could detect the constant acceleration of gravity alongside the louder, shifting accelerations of motion. While a standalone MEMS gravimeter may not yet match the absolute precision of its quantum counterpart, its advantages are profound. It is phenomenally small, often no larger than a postage stamp, incredibly cheap to mass produce, and rugged enough to withstand significant shock and vibration. This opens the door to a future where not just one, but dozens of these tiny sensors could be distributed across a single drone or a massive fleet, creating an even denser and more resilient web of measurements for a fraction of the current cost. This relentless trend of miniaturization, from the refrigerator-sized lab instrument to the chip-based sensor, is the unsung hero that made the entire concept of momentum drone fleets feasible. It transformed the gravimeter from a stationary ground-based observatory into a mobile, airborne probe. This hardware evolution directly enables the three critical attributes needed for a successful drone-based survey: low payload weight for extended flight times, minimal power draw to preserve battery life, and sufficient ruggedness to endure the rigors of flight without constant recalibration. As these sensors continue to shrink and become even more power efficient, the capabilities of the fleets that carry them will expand exponentially. We can envision longer endurance missions, smaller and more agile drones capable of navigating complex terrain like forest canopies or urban canyons, and a dramatic reduction in the cost per survey that will make this powerful technology accessible to smaller nations, academic institutions, and even environmental watchdog groups. The physical shrinking of the sensor has, in a very real sense, massively expanded our ability to see and understand our planet. If the sensitive gravimeters and inertial navigation systems are the fleet's eyes and sense of balance, then the software and algorithms are its brilliant analytical brain. This is where the chaotic river of raw numbers streaming from every drone is tamed, translated, and transformed into a clear, three-dimensional story of the world below. The algorithms powering this transformation are a masterful blend of three distinct disciplines. First, they are grounded in advanced physics, incorporating the fundamental laws of gravity and motion to build a mathematical model of what the world should look like. Second, they employ sophisticated signal processing, acting like a powerful digital filter to separate the true geological signal from the overwhelming noise of flight. And third, they increasingly harness the pattern recognition power of machine learning, teaching the system to see familiar shapes and structures in the data that might elude even a trained human eye. This trifecta of capabilities is what elevates the system from a simple data collector to a true silent architect. One of the software's most critical and immediate tasks is a process known as sensor fusion. Imagine trying to understand a conversation in a crowded, noisy room. Your brain automatically fuses the input from your ears with the input from your eyes watching the speaker's lips, filtering out the background chatter to focus on the words. The drone's software performs a similar but far more precise digital feat. It takes the primary gravitational reading from the gravimeter and then precisely synchronizes it with the torrent of data from the inertial navigation system, every recorded tilt, acceleration, and vibration. Using complex mathematical models, the software subtracts the effects of the drone's own motion from the gravimeter's signal. It's a continuous, real-time process of calibration and correction, stripping away the cacophony of flight to isolate the pure, quiet whisper of gravity emanating from the Earth. Without this foundational step, the data would be an unintelligible mess, a recording of the drone's journey rather than the planet's structure. Once the data is cleaned, the software faces its grandest challenge, solving what mathematicians call an ill-posed inverse problem. This is the ultimate detective game. A traditional or forward problem would be straightforward. If you give a physicist the exact dimensions and density of a buried sphere of iron, they can easily calculate the specific gravity signature it would create at the surface. But the drone fleet has the opposite task. It has measured the gravity signature at the surface, and now the software must work backward to deduce the untold number of shapes, sizes, and densities of objects underground that could have collectively caused that exact pattern. The term ill-posed means there is no single, unique solution. Countless different subterranean landscapes could theoretically produce the same set of surface measurements. To solve this, the software uses a family of powerful algorithms, often based on principles of tomography, similar to those used in medical CT scans. It slices the subsurface into a three-dimensional grid of millions of tiny volume pixels or voxels. The algorithm then begins a monumental process of iterative guessing, assigning different density values to each voxel, running a simulation to see what gravity pattern that model would produce, and then comparing it to the real-world data. Over millions of calculations, it continuously tweaks the model, refining it until the simulated gravity field and the actual measured one align as perfectly as possible. This computational heavy lifting is what conjures the final, vivid, three-dimensional gravity map from a sea of abstract numbers. The latest revolution in this cognitive center is the integration of machine learning. Instead of relying solely on brute force computation, scientists are now training deep learning models on vast libraries of existing geological data and their corresponding gravity signatures. Think of it as giving the software a seasoned geologist's intuition. After being shown thousands of examples, the machine learning model learns to recognize the subtle fingerprints of specific geological features. It can automatically flag the distinctive signature of a salt dome, often a trap for oil and gas, or highlight the linear pattern of a fault line deep within the crust. This doesn't replace the traditional physics-based algorithms but works in concert with them, dramatically speeding up the initial interpretation. What might take a human analyst days to identify, the the machine can highlight in seconds, reducing human error and allowing geophysicists to focus their expertise on the most complex and promising anomalies. The software is evolving from a powerful calculator into an intelligent collaborator, learning the language of the Earth itself and helping us read its hidden texts with ever greater speed and accuracy. This powerful cognitive center, capable of revealing so much, naturally leads us to a crucial and necessary conversation about the responsibility that comes with such profound insight. The ability to peer beneath the surface of the Earth is an extraordinary power, and like any powerful tool, it comes with a profound responsibility to consider its broader implications. As these fleets of silent architects become more common, their constant aerial presence begins to intersect with the age-old concept of privacy. While their primary mission is to map the gravitational field deep underground, the drones themselves are flying through public airspace, often equipped with standard navigation cameras and telemetry systems. This creates a complex situation. A landowner might reasonably question what information is being collected as a drone flies over their private property, even if the core scientific data is subsurface. The concern isn't that the drones are taking high-resolution photographs of backyards, but rather about the principle of persistent, automated observation. This becomes especially sensitive when surveys are conducted near secure facilities, protected indigenous lands, or other areas where even the knowledge of data collection could be considered intrusive. The very act of mapping, even if its focus is invisible to the human eye, can feel like an intrusion when it's conducted without clear communication and consent. This necessitates a new social contract for this technology, one that prioritizes transparency. Operators must be forthright about their missions, publicly defining what data is collected, how it is anonymized and secured, and who has access to it. Clear boundaries must be established, perhaps through geofencing that automatically restricts data collection over specific, sensitive surface coordinates, ensuring that the quest to understand the ground below does not come at the cost of eroding trust with the people living on the surface. Beyond the social contract, we must also consider a literal, environmental one. The vision of a quiet, electric drone fleet seems inherently green, especially when compared to the rumbling seismic trucks and heavy machinery of traditional surveys. However, operating at a large scale introduces its own ecological footprint that must be acknowledged and minimized. The most immediate impact is acoustic. While a single drone might produce a gentle hum, a coordinated swarm of dozens or hundreds can generate a significant and persistent layer of noise over a survey area. For wildlife, particularly in pristine natural habitats, this unfamiliar sonic presence can be a source of chronic stress, disrupting essential behaviors like breeding, foraging, and communication. Bird species that are sensitive to disturbance could be driven from nesting grounds, and large mammals might alter their migration routes to avoid the constant buzzing. Responsible deployment means conducting thorough ecological assessments before a survey, identifying critical habitats and sensitive seasons, such as breeding or nesting periods, and scheduling flight operations to avoid them. It also involves researching and developing even quieter propeller and motor technologies, pushing the industry toward a future where the drones are not just silent in their data collection, but also in their physical presence. The environmental consideration extends far beyond the immediate airspace to the energy required to power this entire enterprise. A single drone has a limited flight time, often dictated by current battery technology. For a large-scale survey, this means a constant cycle of landing, charging, and relaunching, which requires a substantial amount of electricity. When this power is drawn from a grid that relies on fossil fuels, the carbon footprint of the operation can become substantial. Furthermore, the computational heavy lifting required to process the terabytes of raw data into 3D maps is done in energy-hungry data centers, which have their own significant environmental impact due to their massive cooling and power needs. To truly be a force for good, the industry must commit to powering its operations sustainably. This means field teams using portable solar arrays or other renewable sources to charge their drone fleets in remote locations, and companies opting for cloud computing providers that are powered by renewable energy. The goal is to create a closed loop where the technology used to understand and protect our planet does not itself contribute to its degradation. This holistic view of the life cycle of the technology, from the power source to the final data product, is a non-negotiable aspect of its ethical development. Navigating this complex landscape of privacy and environmental stewardship is not a task that can be left to individual companies or research teams. It requires the proactive establishment of clear, forward-thinking ethical guidelines and regulatory standards. These frameworks should be developed through collaboration between technologists, ethicists, environmental scientists, legal experts, and community representatives. They need to address critical questions. What are the minimum necessary data protocols to protect individual privacy? What are the mandatory environmental safeguards for operating in sensitive ecosystems? How do we ensure equitable access to the benefits of this technology while preventing its misuse? Creating these standards is not about stifling innovation. On the contrary, it is about building a foundation of public trust that will allow the technology to flourish and be widely accepted. By openly confronting these ethical challenges head-on, the scientific and industrial communities can demonstrate that their commitment to discovery is matched by a commitment to responsibility. This proactive approach is the key to ensuring that the silent architects are welcomed as partners in progress, not viewed as invasive intruders, securing their social license to operate and paving the way for their boundless potential to be realized for the benefit of all. The groundbreaking work of these silent architects here on Earth is merely a dress rehearsal for their most ambitious performance yet, one that takes them far beyond our atmosphere and into the vast theater of our solar system. The very same principles of coordinated momentum and precise gravimetry that reveal our planet's hidden aquifers and ore bodies are now being adapted for interplanetary missions, transforming how we will explore and understand our celestial neighbors. NASA, the European Space Agency, and other leading space organizations are actively developing concepts where swarms of small, autonomous drones will become the primary geologists for worlds we cannot easily tread upon. This isn't science fiction, it's the logical next step in robotic exploration, moving from single, fragile rovers that study a single dusty patch to dynamic fleets that can map the global subsurface of an entire moon or asteroid from the sky. The challenges of operating on other worlds are immense, but the potential rewards are nothing less than revolutionary, promising to answer some of humanity's oldest questions about the cosmos. Consider the red planet Mars. For decades, orbiters have detected tantalizing evidence of vast deposits of water ice hidden just beneath the surface in its mid-latitudes. This water is the key to any future human presence, a vital resource for life support and for creating rocket fuel. But where exactly is it? How deep does it lie? And in what concentration? A single rover can dig one small trench. A coordinated drone fleet, however, could sweep across the Martian plains, their gravimeters mapping the subtle density differences between rock and ice. They could create a three-dimensional atlas of the Martian subsurface, identifying the most accessible and purest ice reservoirs for a future crewed mission to target. This would turn a desperate hunt for water into a strategic, data-driven excavation, dramatically de-risking the entire endeavor of establishing a permanent outpost on another world. The drones would be the pathfinders, the advanced scouts that ensure the first human footsteps on Mars are taken near a guaranteed source of the most precious resource in the universe. The vision becomes even more profound when we set our sights on the icy moons of the outer solar system, particularly Jupiter's Europa and Saturn's Enceladus. These enigmatic worlds are believed to harbor global, liquid water oceans hidden beneath shells of ice many kilometers thick. These dark, subsurface seas are among the most promising places in our solar system to search for extraterrestrial life. But how do you study an ocean you cannot see or touch? A single lander that melts through the ice would be an incredible feat, but it would provide data from only one single random point. A swarm of gravity-mapping drones deployed from an orbiting mothership could change everything. Flying in precise formation over the fractured, icy terrain of Europa, they would map the moon's gravitational field in exquisite detail. The data would reveal the thickness of the ice shell, identifying where it is thinnest and most accessible. More importantly, it could detect the gravitational signature of the subsurface ocean itself, and even map underwater features like seafloor mountains or hydrothermal vents, potential oases for life. This information would be absolutely critical for selecting a landing site for a future life detection mission, guiding a probe to the location with the highest probability of finding biological signatures. The silent architects would become our remote sensors on a world where direct contact is, for now, impossible. Even small, irregularly shaped bodies like asteroids and comets represent a perfect application for this technology. These cosmic leftovers are time capsules from the dawn of the solar system, but their weak and uneven gravitational fields make them incredibly difficult to navigate. We've seen this challenge firsthand with missions like OSIRIS-REx, which had to carefully map the asteroid Bennu before attempting a brief touch-and-go sample collection. A single spacecraft must spend months in a delicate dance to characterize such a body. Now envision a fleet of small, disposable drones released from a main spacecraft. They could swarm an asteroid, their coordinated momentum allowing them to map its lumpy, chaotic gravitational field from every angle in a matter of days. This high-resolution gravity map would instantly reveal the asteroid's internal structure. Is it a solid chunk of rock or a loose pile of rubble barely held together by gravity? Understanding this composition is vital for planetary defense, as it determines how we might one day deflect a hazardous asteroid on a collision course with Earth. It also tells us where the most valuable minerals might be concentrated, guiding future asteroid mining operations. For pure science, it provides a window into the very building blocks of the planets. In this context, the drone fleet acts as a form of celestial cartography, drawing the first true maps of worlds that have never known a map before. This expansive future, where the silent architects of Earth become the pioneers of interplanetary exploration, represents a fundamental shift in our approach to space science. It moves us from slow, sequential, single-point measurements to rapid, simultaneous global surveys. This technology could indeed become the standard for the initial remote geological assessment of any solid body we encounter, providing a comprehensive understanding before we ever commit to a risky landing. The data they return will be the foundational layer for every mission that follows, from selecting the site of the first human base on Mars to choosing where to drill for alien microbes on Europa. The legacy of these fleets will be written not in the geological maps of Earth, but in the star charts that guide humanity's next great journey into the cosmos. Yet for all this breathtaking potential, The path from terrestrial success to interplanetary deployment is paved with a formidable array of present-day technical hurdles that must be systematically overcome. Despite the breathtaking potential of these silent architects, they are not yet omnipotent. Like any pioneering technology, they operate within a set of very real and demanding constraints that define the current frontier of their capabilities. Perhaps the most immediate and tangible limitation is the finite energy stored within their batteries. The delicate dance of coordinated flight, the constant hum of sensors, and the real-time data transmission are all power-hungry activities. Even with the most advanced lithium-based batteries available today, a typical survey drone might only remain aloft for an hour, perhaps two, before it must return to base for a recharge. This creates a fundamental operational tempo. For a large-scale survey spanning hundreds of square kilometers, this means a constant logistical ballet of launching, landing, and swapping drones, with the entire fleet effectively grounded for significant periods. This battery ceiling not only limits the geographical scope of a single mission, but also impacts the quality of data in a more subtle way. The gravimeter's sensitivity can be affected by slight changes in temperature, and the repeated heating during flight and cooling during charging can introduce minor calibration drifts that must be carefully managed between sorties. The quest for longer endurance is therefore not just about convenience, it's about achieving the continuous, stable data streams needed for the most precise four-dimensional models of our changing planet. Adding another layer of complexity is the challenge of maintaining a flawless digital conversation across the fleet. The intricate coordination of a drone swarm relies on a constant, high-bandwidth exchange of data, positional information, velocity vectors, and synchronization signals. This network is the digital nervous system that binds the individual units into a single, intelligent organism. However, this system is vulnerable to interference, especially in the very environments where we often need these maps the most: dense urban canyons and rugged, high-relief terrain. In a city, the radio spectrum is a crowded and noisy place, filled with signals from Wi-Fi networks, cellular towers, and other communications infrastructure that can drown out the critical links between drones. Among towering skyscrapers, signals can bounce and create multi-path interference, where a drone receives the same message at slightly different times, confusing its navigation. In mountainous areas or deep valleys, the simple line of sight required for reliable communication can be broken by a ridge or a peak, potentially isolating a drone from the swarm. A single lost link can break the formation's integrity and compromise the differential measurements that are the source of its superior accuracy. Ensuring robust, jam-resistant, and terrain-agnostic communication is a monumental engineering hurdle that stands between current capabilities and the vision of truly ubiquitous, reliable subsurface mapping. Then there is the sheer computational mountain that must be climbed after the drones have landed. The raw data harvested by a single fleet mission is staggering, often amounting to multiple terabytes of information. Processing this deluge into a clean, usable 3D gravity map is a task that can tie up a supercomputer for days. The algorithms must perform billions of calculations to solve the inverse problem, iteratively refining the subterranean model until it matches the observed gravity field. This creates a significant delay between data acquisition and insight, a lag that can be problematic for time-sensitive applications like monitoring a rapidly depleting aquifer or assessing ground stability after a major earthquake. The immense power consumption of the data centers that run these computations also contributes to the technology's overall environmental footprint. This processing bottleneck means that, for now, the full potential of the data is not realized in real time. The vision of a live, updating 3D map of the subsurface, where changes are visualized as they happen, remains a future goal, contingent on breakthroughs in computational efficiency and speed. Finally, these sophisticated systems remain at the mercy of the ancient and unpredictable force of weather. While they can be programmed to handle a gentle breeze, high winds pose a dual threat. Firstly, they present a direct physical danger, pushing the lightweight drones off their precise flight paths and risking mid-air collisions. Secondly, and more insidiously, strong gusts degrade the quality of the scientific data. The gravimeter and inertial navigation system are designed to cancel out the drone's normal flight motions, but violent, turbulent buffeting creates a chaotic noise floor that can be difficult to filter out completely. A survey flown on a windy day might produce a map that is fuzzy and filled with artifacts, masking the subtle gravitational signals of interest. Icy conditions can coat the drone's wings and propellers, and heavy rain can interfere with sensors. This weather dependency introduces a layer of uncertainty into project planning, as missions in many parts of the world must be scheduled around seasonal weather patterns, potentially creating long waits for the right window of opportunity to open. Confronting these hurdles has become a central focus for researchers and engineers, sparking a wave of innovation aimed at pushing the boundaries of what's possible. The race for better batteries is exploring new chemistries beyond lithium, such as solid-state designs that promise higher energy density and faster charging times. In parallel, engineers are developing hybrid power systems that combine a conventional battery with a small, efficient hydrogen fuel cell or a microgenerator, potentially extending flight times from mere hours to entire days. To tackle the communication problem, new protocols using adaptive frequency hopping and mesh networking are being tested. In a mesh network, if one drone loses its direct link to the base station, it can relay its data through neighboring drones, creating a resilient, self-healing web of communication that can navigate urban and topographic obstacles. Perhaps the most promising shift is the move towards edge computing. Instead of streaming all raw data back to a central cloud, powerful, miniaturized processors are being installed on the drones themselves. This allows for preliminary data cleaning and compression to be done in flight, drastically reducing the bandwidth needed for transmission and the computational load on the back end. Some of these onboard systems are even becoming smart enough to perform a basic initial analysis, alerting operators to significant anomalies while the drones are still in the air. Acknowledging and systematically overcoming each of these technical hurdles is not a sign of weakness in the technology. It is the very engine of its evolution, a testament to the relentless pursuit of a clearer, deeper, and more responsive vision of our world. To truly appreciate the power of these silent architects, let's journey to a remote and rugged mining concession in a place like the Canadian Shield or the Australian outback. A major mining company held the rights to a vast 500 square kilometer parcel of land. Geological surface clues and broad regional data suggested the area had high potential for a valuable base metal deposit, perhaps rich in copper, zinc, and gold. But the terrain was a formidable challenge, a dense boreal forest interspersed with rocky outcrops and swampy ground, making traditional exploration a logistical nightmare. The conventional approach would have been to send in a team of geophysicists on foot or in all-terrain vehicles, armed with heavy gravimeters. They would have had to clear survey lines through the brush, stopping every few hundred meters to take a painstaking, stationary measurement. This ground-based method, while reliable in its own right, was projected to take a dedicated team over 6 grueling months to complete, with a total cost running into the millions of dollars just for the initial data collection, not to mention the exposure of field crews to the elements and potential wildlife. It was a slow, expensive, and physically demanding gamble. the company decided to take a different path, partnering with a specialist firm to deploy a fleet of 20 autonomous drones. The operation began with surveyors defining the precise flight grid, a task completed in a matter of days rather than weeks. Then the swarm was launched. For 2 weeks, the drones executed their silent, coordinated ballet over the wilderness. Flying in a pre-programmed formation, they maintained their precise momentum states, their gravimeters and inertial navigation systems working in perfect harmony, collecting millions of individual data points without ever disturbing the fragile ecosystem below. There was no need to clear trees or build access roads. The drones simply flew their patterns, landed autonomously for battery swaps, and relaunched, operating nearly around the clock. Where a ground crew would have been bogged down by impassable swamps and sheer rock faces, the fleet soared overhead unimpeded. In just 14 days, they captured a complete, high-resolution gravitational picture of the entire 500 square kilometer area. A task that had been estimated to take half a year was now finished before a traditional team would have even completed their initial mobilization. When the data was processed through the sophisticated fusion pipeline, the results were nothing short of spectacular. The final 3-dimensional gravity map rendered on the geologist's screens was a masterpiece of clarity. The background rock showed as a sea of cool, uniform colors, but leaping out from the center of the survey area was a brilliant, warm-hued anomaly. This was a clear signature of high density, a subterranean bullseye located at a depth of approximately 300 meters. The shape and intensity of the gravitational signal suggested a large, coherent body, precisely the kind of target that could host a massive sulfide ore deposit. This wasn't a vague hint or a subtle suggestion. It was a definitive, 3-dimensional object revealed in vivid color. The map provided the company's exploration team with a level of confidence they had never before possessed at such an early stage. They could see the target's lateral extent, its depth, and even infer its general shape, allowing them to plan the next phase with surgical precision. That next phase was the ultimate test, the drill rig. Armed with the precise coordinates from the gravity map, the company moved a diamond drill rig to the exact location. There was no guesswork, no exploratory wildcat drilling. The first hole was planned to intersect the heart of the anomaly at 300 meters. As the drill core was pulled to the surface, the excitement was palpable. The initial sections showed only the expected barren host rock, but as the drill bit passed the 280-meter mark, the character of the core changed dramatically. The geologists on site began to pull up long, solid cylinders of rock heavily mineralized with shiny, metallic sulfides, a textbook example of a volcanogenic massive sulfide ore body. Lab analysis later confirmed high concentrations of copper, zinc, and significant traces of gold and silver. The discovery was an unqualified success, a company making find that would lead to the development of a highly profitable new mine, creating hundreds of jobs and generating substantial economic value for decades. The entire discovery timeline, from the start of the aerial survey to the confirmation by drilling, was compressed from what could have been a year-long process into a matter of a few months. This single case study crystallizes the transformative impact of this technology, demonstrating a paradigm shift in both speed and accuracy. The velocity of discovery is perhaps the most immediate benefit. What used to be a seasonal, plodding endeavor has been accelerated to the speed of modern data processing. This speed translates directly into massive cost savings and a decisive competitive advantage. But even more critical than the speed is the profound leap in accuracy. The traditional method produced a sparse set of data points that required extensive interpretation and interpolation, leaving ample room for error. The drone fleet, however, delivered a continuous, high-fidelity image of the subsurface. It didn't just suggest where to look, it showed geologists exactly what they were looking for and precisely where to find it. This shift from inference to observation dramatically de-risks the entire exploration process, turning a high-stakes gamble into a strategically guided investment. It proves that the silent architects are not merely an incremental improvement but a fundamental reinvention of how we discover the resources that build our world, a success story that now demands an equally modern and responsive regulatory framework to guide its widespread adoption. Integrating these sophisticated drone fleets into the skies above us is a regulatory puzzle as complex as the technology itself. Aviation authorities around the world are currently in a race against time, drafting and implementing new rules to govern what is known as Beyond Visual Line of Sight, or BVLOS, operations. The foundational principle of traditional aviation has always been see and avoid, a rule that hinges on a pilot's direct vision from the cockpit. This model completely shatters that paradigm. A single human operator cannot possibly maintain visual contact with a swarm of dozens of drones spread across miles of airspace. The new regulatory frameworks must therefore create a digital equivalent of see and avoid, a system where safety is guaranteed not by human eyes, but by a combination of sophisticated technology and robust procedural controls. This involves mandating that each drone is equipped with advanced detect and avoid systems, which function like a digital co-pilot. Using a combination of radar, LiDAR, and optical sensors, these systems can automatically sense other aircraft, birds, or obstacles and execute evasive maneuvers long before a human operator would even be aware of a potential conflict. This technological mandate is the first and most critical layer in building a safe, integrated airspace. Beyond the technology on the drones themselves, regulators are grappling with the monumental task of managing this new form of traffic. Imagine the airspace over a major city or a busy resource exploration area, not just with passenger jets and helicopters, but with multiple, simultaneous drone fleet operations from different companies, all conducting their own intricate aerial ballets. Without a centralized traffic management system, this would be a recipe for chaos. This has led to the development of unmanned aircraft system traffic management, or UTM, platforms. Think of UTM as an air traffic control system designed specifically for drones, but one that is largely automated and digital. Before a fleet is deployed, its operator would file a digital flight plan with the UTM system, detailing the exact area, altitude, and duration of the operation. The system then acts as a central clearinghouse, ensuring that no two authorized flights overlap in a dangerous way. It dynamically allocates airspace corridors and provides real-time updates on temporary flight restrictions, such as those around airports, emergency response operations, or major public events. This digital orchestration is essential to prevent mid-air collisions and to ensure that the skies remain safe for all users, both manned and unmanned. A crucial component of this regulatory framework is the clear and enforceable definition of no-fly zones. These are not just the obvious spaces around airports and military bases. The regulations must also protect sensitive locations like power plants, critical infrastructure, and national borders from unauthorized surveillance or interference. Furthermore, they must address the legitimate privacy concerns of citizens by potentially restricting persistent low-altitude flights over residential neighborhoods. Establishing these zones is one thing, enforcing them is another. This is where geofencing technology comes into play. Geofencing creates a dynamic, virtual cage using GPS coordinates. A drone is programmed with a digital map that includes all permanent and temporary no-fly zones. If a drone, whether through pilot error, system failure, or malicious intent, approaches one of these restricted boundaries, the geofencing software will prevent it from entering. It can first issue a warning to the operator, then automatically slow the drone's progress, and if necessary, command it to land immediately. This proactive, software-based enforcement is a key tool for regulators, providing a layer of security that doesn't rely solely on the hope that operators will follow the rules. The successful creation of this entire ecosystem hinges on an unprecedented level of collaboration. It cannot be a top-down decree from aviation authorities alone, nor can it be driven purely by the demands of technology companies. A three-way partnership is essential. Technology developers must work hand in hand with regulators, providing transparent access to their systems so that safety standards can be rigorously tested and validated. Industry users, from mining conglomerates to environmental agencies, must clearly communicate their operational needs and real-world challenges, helping to shape regulations that are both practical and effective. And government agencies must be willing to adopt a flexible, iterative approach to rulemaking, creating sandbox environments where new technologies can be safely tested and where regulations can evolve alongside the capabilities of the drones themselves. This collaborative spirit is the only way to build a regulatory environment that does not stifle innovation with overly burdensome restrictions, but instead fosters it by providing the clear rules and safety assurances needed for widespread investment and adoption. Navigating this complex bureaucratic airspace is therefore just as critical to the success of this technology as navigating the physical and computational challenges. It is the foundational work that will allow the silent architects to operate safely and seamlessly in our skies, unlocking their full potential to map our world. And behind every line of regulation, every algorithm, and every flight path, there is a profoundly human story of curiosity and dedication. Behind every autonomous drone and every line of intelligent code, there is a vibrant and diverse collective of human minds, a modern-day orchestra of expertise where each individual plays a distinct and vital instrument. The geophysicist is the initial visionary, the one who stands before a vast, uncharted landscape and asks the fundamental question that sets the entire mission in motion. They look at a mountain range and wonder about the tectonic forces that built it, or they study a drought-stricken plain and seek to understand the hidden geometry of its aquifers. Their deep knowledge of the Earth's history and processes defines the mission's scientific objective, translating a grand geological mystery into a specific, measurable goal for the fleet to solve. They are the keepers of the why, ensuring that the technology is directed toward questions of genuine importance, whether for scientific discovery, resource security, or environmental stewardship. Working in close partnership with the geophysicist is the aerospace engineer, the master of the physical realm who transforms a theoretical mission into a robust flying reality. Their challenge is a constant battle against the elements and the laws of physics. They must design a platform that is light enough for extended flight, yet strong enough to withstand turbulence. They select materials that can resist corrosion from sea spray during a coastal survey and electronics that can function reliably in the sub-zero temperatures of the Arctic. Every component, from the shape of the propeller to the placement of the gravimeter inside the drone's body, is meticulously calculated to minimize vibration and ensure the stability required for a clean data collection. The engineer's ingenuity creates the dependable physical vessel that carries our senses into the sky, a testament to practical problem-solving that makes the entire ambitious endeavor possible. Then comes the software developer, the architect of the fleet's digital consciousness. If the drone is the body, the code is its nervous system and brain. These programmers operate in a world of abstract logic and complex algorithms, writing the millions of lines of code that govern everything from the swarm's graceful formation flight to the real-time sensor fusion that strips away the noise of motion. They don't just write commands, they encode behaviors, creating the rules for swarm intelligence that allow individual drones to act as a cohesive, resilient unit. Their work is a blend of art and science, building a digital world where autonomy, safety, and efficiency coexist. A single flaw in their logic could lead to a mid-air collision or a corrupted data stream, so their focus and precision are as critical as any physical engineering, crafting the invisible intelligence that guides the silent architects. Once the data streams in, the data scientist takes the stage, the digital alchemist who transforms a torrent of raw numbers into a coherent story. They face an overwhelming flood of information, endless columns of gravitational readings, positional coordinates, and inertial measurements. Their toolkit is filled with advanced statistical models, machine learning algorithms, and visualization techniques. They are detectives of patterns, sifting through the digital noise to find the subtle gravitational whispers of a buried ore body or the faint signature of a shifting aquifer. They don't just process data, they interpret it, asking the algorithms to reveal the hidden structures that the human eye could never perceive. Their final creation is the stunning, color-coded 3D map that makes the invisible visible, a visual narrative that allows the geophysicist to finally answer the question they first posed. This seamless collaboration, from the geophysicist's initial curiosity to the data scientist's final revelation, is the true engine of progress. It is a powerful reminder that technology, no matter how autonomous it appears, is never a replacement for human ingenuity. Instead, it is its greatest amplifier, a tool that extends our innate curiosity and capability to perceive our world in ways we once thought were the domain of dreams. This drive toward a unified understanding of our planet has naturally fostered a powerful culture of global collaboration. The challenge of mapping Earth's gravity is simply too vast for any single nation to tackle alone. The silent architects, by their very nature, collect data that paints a picture of a dynamic, interconnected system shifting tectonic plates, global water cycles, and melting ice sheets that affect sea levels worldwide. These processes pay no heed to the political lines we draw on maps. Recognizing this, international scientific bodies like the International Association of Geodesy have become crucial facilitators, creating frameworks that allow data from national drone fleet projects in the United States, the European Union, Japan, and elsewhere to be shared, standardized, and seamlessly combined. This isn't just about pooling resources, it's about creating a single, coherent language from which we can read the planet's story. When gravitational data from a German fleet surveying the North Sea is combined with measurements from a Japanese team over the Pacific and a Brazilian initiative in the Amazon, the result is something far greater than the sum of its parts, a unified, high-resolution global gravity model. This model becomes a foundational dataset, a common reference that elevates the work of every scientist who uses it, ensuring that a discovery in one part of the world can immediately inform research in another. Fueling this collaborative spirit are powerful open data initiatives that are fundamentally changing the pace of scientific discovery. Institutions such as NASA and the European Space Agency have led the way, making vast amounts of satellite-based gravitational data freely available to the global research community. This philosophy is now being extended to the incredibly rich datasets produced by these drone fleets. By placing this information in open-access repositories, we remove the traditional barriers of cost and institutional access that have often slowed down progress. A graduate student at a university in Kenya can now download the same detailed subsurface maps of a watershed that are available to a senior researcher at a prestigious lab in Switzerland. This democratization of data unleashes a torrent of collective brainpower. It allows for independent verification of findings, encourages novel interpretations, and enables the kind of large-scale, meta-analysis that can reveal planetary trends too subtle for any single study to detect. The true power of open data is its multiplicative effect. One dataset can be the key that unlocks a dozen different research questions in a dozen different fields, from agronomy to volcanology. This global, open approach is the bedrock upon which we are building our response to some of humanity's most pressing challenges, with precise sea level rise monitoring standing as a prime example. Predicting how coastlines will change is not a matter of simply adding meltwater to a bathtub. It requires an intricate understanding of how the loss of ice mass from Greenland and Antarctica alters the Earth's gravitational field and rotates its axis, leading to an uneven distribution of sea level rise across the globe. To model this with the accuracy that coastal cities desperately need for their planning, scientists require a constant, global stream of gravitational data. No single country's drone fleet can monitor the entire cryosphere, but a collaborative international network can. By sharing data across borders, researchers can create a near real-time dashboard of planetary change, tracking the gravitational pulse of the ice sheets with a precision that was unimaginable just a decade ago. This shared intelligence allows for more reliable, localized projections, empowering every nation from the Maldives to the Netherlands with the specific information they need to build resilient futures. It transforms a global threat into a manageable problem addressed with shared tools and a common purpose. This spirit of collaboration underscores a profound truth. Understanding the fundamental forces that shape our planet is not a national competition, but a shared human endeavor. It's a pursuit that transcends political borders and historical conflicts, uniting us in the common goal of comprehending our home. The silent architects, the drone fleets themselves, are the powerful tools that make this global perspective not just an ideal, but a practical reality. They provide the objective, quantitative data that forms a universal language, a set of facts upon which everyone can agree. In a world often divided, this shared quest for planetary knowledge represents a beacon of international cooperation, demonstrating that our greatest achievements often arise not from isolation, but from the open exchange of ideas and information. As this global community of researchers, engineers, and analysts continues to expand and interconnect, it creates a powerful demand for a new kind of expert, one who is as comfortable with international collaboration as they are with complex data, highlighting a critical need to cultivate the next generation of talent. This technological leap is creating a fascinating and urgent challenge in the job market, one that reaches far beyond simply needing more drone pilots or data analysts. We are witnessing the birth of an entirely new profession, a hybrid expert who can speak the distinct languages of several complex fields at once. Imagine a professional who can stand in a room with a geophysicist and discuss the intricacies of sedimentary basin formation, then turn to a robotics engineer to troubleshoot a flight control algorithm, and finally, collaborate with a data scientist to refine a machine learning model for identifying mineral signatures. This isn't a specialist in one area. It's a master integrator, someone who understands how the geological question dictates the flight pattern, which in turn determines the structure of the data pipeline, and whose final output must be interpreted through the lens of both physics and statistics. The demand for these geospatial polymaths is already surging. but the supply is still catching up, creating a significant skills gap that threatens to slow the pace of innovation if we don't address it proactively. In response, academic institutions worldwide are undergoing their own quiet revolution, tearing down the traditional walls between university departments to build new, interdisciplinary curricula. You won't just find this new training in a single faculty. It's emerging at the intersection of geology, computer science, engineering, and environmental studies. A typical program might see a student in their first year learning the fundamentals of plate tectonics and mineralogy, while simultaneously taking introductory courses in Python programming and calculus. By their third year, that same student could be working on a capstone project where they program a small drone swarm to map a local hillside, process the gravitational data using open-source algorithms, and interpret the resulting map to identify potential landslide risks. These programs are heavily project-based, moving away from pure theory and plunging students into the messy, rewarding reality of solving real-world problems. They are taught not only how to operate the technology, but more importantly, how to think critically about its application, to ask what scientific or industrial question needs answering, and then design a mission from start to finish to provide that answer. This hands-on, integrated approach is crucial for building the practical wisdom and creative problem-solving skills that this field demands. Bridging this skills gap is not merely an educational exercise. It's a strategic imperative for building a workforce capable of not just operating these complex systems, but of continuously pushing them forward. The true potential of this technology will only be unlocked by people who are not just users, but innovators. We need engineers who can look at a current gravimeter and envision a next-generation quantum sensor that is 10 times smaller and 100 times more sensitive. We need data scientists who can develop novel algorithms to solve the inverse gravity problem faster and with greater accuracy, perhaps even in real time. And we need geoscientists who can dream up entirely new applications, using these detailed subsurface maps to track the spread of environmental contaminants or to locate optimal sites for geothermal energy extraction. This requires a deep, foundational understanding that allows for creative leaps. Without a steady pipeline of these deeply skilled professionals, we risk having a revolutionary tool without the visionary minds to guide it towards its most impactful uses. The next generation of silent architects won't just be the drones humming in the sky. They will be the highly skilled, interdisciplinary human teams on the ground. The geospatial strategists, the autonomy engineers, the computational geophysicists who design the missions, interpret the results, and dream of the next great question to ask of the planet. Their expertise is the true engine that will ensure this transformative field continues to advance, evolving from a powerful mapping tool into an indispensable part of how we understand and steward our world. Stepping back from the individual applications, the true magnitude of this shift comes into focus. Momentum drone fleets are not merely providing us with better maps, they are gifting humanity an entirely new sensory organ for the planet, a way of perceiving that was previously beyond our biological capabilities. For our entire history, we have been surface dwellers, interpreting the Earth almost exclusively through light and sound, what we can see with our eyes and hear with our ears. We mapped mountains and valleys, observed the flow of rivers, and classified rocks based on their surface color and texture. But this was always a superficial understanding, like trying to comprehend a person's health by only looking at their clothes. The real substance, the mass and density that define the planet's structure and its dynamic processes, remained a profound mystery hidden in the dark, silent depths below. This new gravity lens shatters that limitation, allowing us to perceive the world through the fundamental force that sculpts it, revealing the architecture of mass that has been concealed since the planet's formation. This new sense reveals a world that is astonishingly dynamic and alive in its hidden dimensions. We are no longer looking at a static landscape, but observing a planet in constant, slow-motion flux. Through this lens, we can witness the pulse of the hydrologic cycle in a way that was once impossible. It's not just about knowing that an aquifer exists. It's about watching its mass increase as seasonal rains percolate down through the soil, and then seeing that mass gradually diminish over a dry summer as farmers draw water for their crops. We can track the slow, gravitational ebb and flow of water across entire continents, a silent, subsurface tide that dictates the prosperity of nations. On a grander, more powerful scale, this perception lets us feel the immense, churning forces of plate tectonics, the colossal grinding of tectonic plates, the descent of a slab of oceanic crust into the mantle at a subduction zone, and the buoyant rise of magma plumes from the deep earth. All of these processes create subtle but detectable shifts in our planet's gravitational field. We are moving from theoretical models of these systems to direct quantitative observation, watching the planet's engine at work in real time. This shift from qualitative guesswork to quantitative certainty marks a revolution in Earth science. Before, our understanding was often pieced together from scattered, indirect clues, a rock type here, a fossil there, a single well log from a distant location. It was a scientific narrative built on inference. Now, the gravity lens provides a continuous stream of hard numbers, a three-dimensional data field of density values that can be analyzed, modeled, and tested with mathematical rigor. This data doesn't just confirm existing theories, it constantly refines them, revealing complexities and nuances we never anticipated. It allows us to move beyond simple questions like, is there water here? To profoundly more detailed ones like, what is the total volume of this aquifer? How has it changed over the past 5 years? And what is its flow rate through the surrounding rock? This quantitative, holistic grasp of Earth systems transforms our relationship with the planet from one of passive inhabitant to active, informed steward. We are building a digital twin of the Earth's subsurface, a dynamic model that we can use to simulate the consequences of our actions, from pumping groundwater to constructing massive infrastructure with unprecedented foresight. Ultimately, this is far more than a simple technological upgrade, another incremental step in a long line of scientific instruments. It represents a fundamental expansion of human perception itself. For millennia, our understanding of reality was bounded by the limits of our biological senses. We built tools like telescopes and microscopes to extend our sight, but they still worked within the same electromagnetic spectrum. The gravity lens operates on an entirely different principle, allowing us to perceive a fundamental force of nature directly. It is akin to a species that has only ever known sight and sound suddenly developing the ability to perceive magnetism or radioactivity. This new sense is rewriting the textbook of our planet, not by adding a new chapter, but by providing a way to read the entire book for the first time, revealing a hidden narrative of mass, movement, and energy that has been unfolding beneath our feet all along. It is a profound leap in our cognitive and sensory engagement with the world, granting us a deeper, more intimate connection to the living, breathing planet we call home. The silent architects of momentum are quietly reshaping our relationship with the planet, translating the invisible pull of gravity into a detailed, three-dimensional canvas of understanding. We've journeyed from their core technology to their profound impacts on resource security, climate science, and infrastructure safety. This is not the end of the story, but the beginning of a new chapter in geospatial intelligence. As these fleets become more advanced and widespread, their maps will become the foundational layer upon which we build a more sustainable and resilient future. The greatest discoveries often lie not in what we can see, but in learning to see what was always there. We encourage you to share your thoughts on this incredible technology in the comments below and subscribe for more explorations into the frontiers of futuristic technology.